we are going to get formally introduced to a rational function. A rational function is when you have a polynomial on the top and a polynomial on the bottom. And we are going to formally look at the characteristics of rational functions and how they're going to help us graph. We informally saw these characteristics when we did 2.2 and saw the different groups. Okay? Now, more formally, the first thing that you're always going to do when you have a rational function is you are going to factor it completely. This function has already been factored completely for us. Then you're going to look at the non-permissible values. Non-permissible values are always things that would cause you to divide by 0. In this case, x couldn't equal 3, and x couldn't equal -1. Those would be your non-permissible values. And non-permissible values will either end up being wholes or vertical asymptotes. They will be vertical asymptotes if they don't simplify, and wholes if they simplify. So in this situation, both the -3 and the x plus 3, they're not identical. That doesn't simplify. Nothing would simplify here. Your non-permissible values stay. We would say that this one has vertical asymptotes at x equals 3 and x equals -1. And they've drawn the graph there and added those vertical asymptotes. The non-permissible values can also be wholes. Right? When is it a whole? Well, here we have our non-permissible value that x can't equal 3. But we have the exact same factor on the top and the bottom. When you have the exact same factor on the top and the bottom, and it simplifies, it becomes a whole. In fact, it simplifies, I'm going to write this equation here. It simplifies to just y equals x plus 1. And you will have a whole at the non-permissible value. And this y coordinate of the whole, you can find plug, let's go, let's write it this way, plug your non-permissible value into the simplified equation. So if I plug 3 into the simplified equation, I'm going to get 3, 4. So anytime your non-permissible value simplifies away, it doesn't mean it's no longer a non-permissible value, because in the original equation, you're still not allowed to plug in 3. But when it does simplify away, it becomes a whole. And these are often really easy ones to graph, because once you simplify it, you're like, hey, that's something I already know how to graph. That's a straight line. So what does a straight line look like? Well, I add my y-intercept, I add my slope. The only thing different in this straight line is that we have to add a whole at 3, 4. Everything else you would do to graph this, you'd do the same. You'd be like, oh, I know my y-intercept is 1. I know my slope is 1, so up 1 over 1, up 1 over 1. Add the whole, draw the graph, and you're fine. There are sometimes situations, not very often, but this next example has non-permissible values. Here's the original equation. Has non-permissible values at x can't equal 3 and x can't equal -1, because that would cause me to divide by 0. Notice that this x minus 3 cancels out with one of the x minus 3's on the bottom. But we still have an x minus 3 on the bottom as a non-permissible value. This one has still only vertical asymptotes. It only becomes a whole if the non-permissible value cancels and it goes away. Because you find the coordinates of the whole by plugging the non-permissible value into the new equation. But if I tried to plug in 3 into that new equation, I'd still have a non-permissible value and something that wasn't positive. Okay. So before we do example 1, we are going to also look at the next characteristics, which is either horizontal asymptotes or oblique asymptotes. And we're going to look at some shortcuts for this because this was really what we looked at in group 1, group 2, and group 3 of section 2.2. This is the easiest one. If your degree is larger in your denominator, this is the easiest one. You will always have a vertical asymptote at y equals 0. Oh, sorry, not vertical asymptote. That should be an H. We're talking about horizontal asymptotes. Why? Well, let's think about extreme values. Let's plug in a very big value for x. You would have a huge number on the bottom and just a -4 on the top. -4 divided by a huge number will get really, really close to 0. So anytime you have your degree larger in the denominator, and again a review, your degree is your highest exponent. In this case it would be an x to the 1. There are no x's in the top, so we would say that the top has a degree of 0, the bottom has a degree of 1. You're going to have a horizontal asymptote at y equals 0. You can use the shortcut. The textbook goes into a little bit more of an explanation. It's not too bad. They're basically saying the same thing. When x gets really, really big, it's going to get close to 0. This is formally how we like to write x gets really, really big. We write x, and then we draw an arrow to infinity. Or you could write x with an arrow to -infinity, either a really big positive number or a really big negative number. They put it in absolute value signs to say both at the same time. So this is one group. The easiest group to find your horizontal asymptote. Degree is bigger in the bottom. Secondly, if the degree is the same in your numerator and your denominator, then you will have a horizontal asymptote at y equals, and I'm going to put this in quotation marks because it's only for this example. You look at the highest degree. In this case, we had a 2x on the top and an x on the bottom. So in our example, it would be at y equals 2. If I did another example, say with a parabola, you see that I have an x squared on the top and an x squared on the bottom. I can ignore, this one will have a horizontal asymptote at, I can ignore everything but the x squared. I'll put it in quotation marks again. And this one would be a 3x squared on the top and a -7x squared on the bottom. horizontal asymptote at 3 over negative 7. So you just look at the coefficients of your highest degree to find your horizontal asymptote. This is the shortcut if the degrees are the same. Again, it's that idea that if I plug in a very big number for x, minusing 3 and minus 1 won't matter. Okay? It's a little bit, in the second example here, like if you added, put in a very big number, look at the top, it's plus 5 times, let's say 1,000,000. 5 times 1,000,000 is like, that's a pretty big deal, especially talking money. But when you compare it to 1,000,000 squared, it's nothing, right? It'd be like, woohoo, you just won the lottery. You won $30 million. You think you're a big deal, and then you go stand beside someone like Elon Musk or someone, the guy that owns Amazon. And how big of a deal are you? You are nothing. It's like, oh yeah? Well, challenge you to donate 100 million to something, and it makes no difference to him. And you're like, I just won the lottery, but I don't even have 100 million. I feel small and insignificant. Even though you're not, like you just won $30 million, but compared to a very big thing, you are small and insignificant. So, yeah, now we can all feel sad, money-wise. So that's the idea here. Again, the textbook actually goes into too much detail. Don't worry about it. Just have to worry about the shortcut here for this, finding your horizontal asymptote by looking at the largest degree. And the last type is when the degree is larger in the numerator and I'm going to write a nothing simplifies, okay? Because we did an example already where the degree was larger in the numerator, but something simplified. That was right here, right? You have an x squared on the top and an x on the bottom, but something simplified and you had a hole, you ended up with a line. There's no asymptotes whatsoever in this one. However, when something does not simplify, you will have an oblique asymptote. I should write it out first time. Oblique is a fancy word for diagonal. And here we use synthetic division to find it. So we actually divide x squared by x plus 1. How do I use synthetic division again? If I have an x squared, I have 1x squared, 0 x's, and 0. So I have 1, 0, 0. If you're dividing by x plus 1, do you remember that you put the opposite symbol out in front? Bring down the 1, multiply, then add, multiply, then add. Then your oblique asymptote, or your division statement, would have an x minus 1. That's your asymptote. And you can ignore the remainder. It has a remainder of 1. Who cares? Could be a remainder of 1 billion. I don't care. How much the remainder is? My oblique asymptote is just what I get after I do synthetic division. Again, the textbook is worried about explaining why that happens. If you are interested in that, go ahead and read some more of why the oblique asymptote happens there. It's basically saying that as you put in something bigger and bigger and bigger and bigger, this is basically going to get closer and closer to this line as its end behaves. So these are the 3 different situations for horizontal and oblique asymptotes. Degree is bigger on the bottom, horizontal asymptote at y equals 0. Degrees are the same horizontal asymptote at the coefficient. If the degree is bigger in your numerator, and nothing simplifies, no holes or anything like that, stay bigger in your numerator, you're going to get an oblique asymptote. So now we're going to go to example 1. And the first thing I'm going to get you to do, because what we're going to do for each of our examples is practice all of our characteristics and graph them completely. So what I would like you to do is to write these steps down. And we're going to use these steps over and over again for a bunch of different situations. And this is the last thing you need to know for this unit. Isn't that crazy?
It is the last.
This is the last thing you need to know for this unit. We're just going to take these 5 steps and apply them to different situations. But we always do them the same way, just the graphs turn out different each time. Yeah. We only have one quiz for this unit. Isn't that crazy? Oh. I think I paused the video while you were writing and I never unpaused it. So that's kind of sucks. There's the final answer. You'll have to watch the other class's video.